So we're going to talk about accumulation functions. So this is kind of new, kind of not new, okay? So basically what we're going to do in the next 3 sections is kind of things that we've already done, but we're going to do them more in depth, okay? So we've already talked about accumulation functions because we've said it many, many times during this chapter about if you're given a rate and then we integrate it, we're going to get the whole thing, like the total. So for example, if it was gallons per minute and I integrated it, I get gallons, okay? So that's the same thing that we're going to do. We're just going to, as I find my paper, because I don't want to refigure all the numbers, but we're going to do it a little bit more in depth. Now, I would triple, quadruple, star this lesson something. After the discussion we just had, I'm sure none of you are ever going to look at it again. However, you should look at it again because it is a pretty sure guarantee that this is on one of the free response questions. So this is a very, 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 very common question, okay? So I would put lots of stars, something on this lesson because it's definitely going to be something that you need to know on the AP test. So it's really obvious what you need to do if they say, oh, we have a rate of change. But they're not going to say that. They're going to say there's water going into this tank at so many gallons per minute. How many gallons are in the tank after 5 hours? Okay, so I need to know that if they give me a rate of change and I'm looking for total whatever, that I integrate it. That's the key. So I think you have that statement actually. Oh, no, it's at the bottom. Okay. So let's talk about this. So this is the illustration.
On the equation it was showing, we had that.
Oh, it should be. Oh, yeah. Well, it should be f prime. Yours should be f prime, too, if it's just f of x. So that should be. Well, no, this shouldn't be f prime. This should be f. Because this is capital F. They're telling you little f is the derivative. That was a fundamental theorem of calculus. The capital F, remember, was our standard for antiderivative. So really that shouldn't say prime, but it should say dx. So that's just a mistake on that. So the key, the really important thing is, though, they don't say prime. That's kind of the key. I need to know that it's technically it's the derivative, okay, because it's a rate of change. That's what I need to know. So here we're going to look at an example, and we're going to go ahead and do these, even though it doesn't say to do it, but it's going to tell you what we're supposed to do, okay? So water is being pumped into a tank at a rate of RT equals square root of T plus 1 gallons per minute. So the very first thing I would have done when I read that question is underline gallons per minute, or even the word rate. I mean, the fact that it's a rate of change, okay? Then the amount that is pumped in the first 5 minutes is going to be this many gallons. I'm going to integrate from 0 to 5. Now remember, we talked about interpreting. So if they just said interpret, so say they just had the first sentence, first part of the sentence, and they said interpret this integral. Remember, on your interpretation, you have to have units over a time interval. So I would have to say that this represents the number of gallons in the first 5 minutes, or over the 0 to 5 minutes, okay? Number of gallons in the tank. So we're going to actually do that. So let's go ahead and do this integral, this indefinite. So how should I rewrite it when I go to this? How should I rewrite square root of T plus 1? Right, because we already know that we do not have a rule for square root, but I do have for powers, so I rewrite it. Now, technically this is use substitution. So let's start moving away from always writing a substitution and see how we don't need to do that here. So what would u be? What's that first thing we're always going to try? The inside, right? T plus 1. But if you let that be u, which we're not going to do, what would du be? 1 dt, would just be dt. So there's no change needed So it really doesn't do me much good to do that. I just need to recognize it's whatever's inside raised to the power divided by the power. I don't need to do anything because du is in fact just dt, so be kind of a waste of my time to rewrite it. So anytime you're going to let something be u and the derivative is exactly already, it's just dt or dx or whatever, there's no reason to write it. You need to get to that point. You may have to make yourself do that a little bit. So in other words, I just have to take t plus 1, add 1 to the power, which would be 3 over 2, and then we're supposed to divide by 3 over 2, but we don't do that. We do multiply by 2/3, and then 0 to 5. This is a definite integral because it has limits, okay? It has limits of integration. Then I need to evaluate it. So if you have to go over to the side, make sure you make an arrow and put enough space. Don't just put an equal sign kind of close to the other part, or it looks like those are connected. So I'm going to get, I always leave the constant out by itself because it's easier than having a bunch of fractions. Just leave 2/3 out, plug in. So what happens when you plug in t? Plug in for 5. 5 for t. 6, and it's just 6 to the 3/2. Just leave it. Don't care. Minus 1 to the 3/2. Here's the part where people mess up. They just assume anytime it's 0, I just put 0. It's not. It's 1 to the 3/2, which is 1. So I'm done. That's a number answer. Now, if this was a calculator question, I wouldn't have even done any of this other stuff, right? I would have just written down the original integral, put it in the calculator, answered the question. So if it's not, which is not, obviously, then I would just leave that answer, okay? Now, it does have units. What are those units? Gallons, because we integrated gallons per minute. Now, the question said, how much is pumped in the first 5 minutes? So I can just answer whatever gallons. But if the question said, interpret the meaning of this integral, I would need to say it is the number of gallons pumped in the first 5 minutes. Because they specifically asked me that, I don't need to say it again, like this many gallons in the first 5 minutes, because that was the question. Okay? All right, so now let's talk about the next one. So we have a car traveling with velocity. Now they put rate in parentheses. You need to know that it's the rate. Why do you know it's the rate? What's velocity? Well, change in distance over position over time, right? So it's a rate of change. This is in miles per hour. So it says miles per hour, okay, is listed. So again, that's a rate, okay? So that tells me this is a rate of change. So if I integrate it, I'm going to get miles. Now, here's the catch, and we need to be careful about with velocity. What do you know about velocity that's a little different than speed? It has a direction. So if I integrate and some of that's underneath, I'm actually going to get displacement. This integral technically is displacement. What makes it distance? What did I have to do? Absolute value of it. Now, why do I not need to do that here? Look carefully at it and think about it. Why is that not necessary, and why do I know this actually does give me the distance? Everything's positive. If you plug in 0, what do you get? 12, and then everything else is positive from 0 to 3, and then you're just adding, right? So there's no negative. So everything's above. So this is all above the x-axis. So we do need to be careful of that. We're actually going to do a whole section to review all that position, velocity, acceleration stuff. Okay, so we'll do a whole section on that to review it, but we've already done some of that. So again, if I want to find the total distance traveled in 3 hours, then I'm going to integrate that. So I need the integral from 0 to 3. We're going to go ahead and do it. So I'm going to write it down. And then we need to go ahead and find the antiderivative. So what's the antiderivative?
T cubed
T cubed over 3 plus
It's 12,
Don't say that.
3t.
3t squared. You've got to learn to substitute. That's okay. That's one of those things I want you to, you've got to learn to do that. Because it's simple little tiny numbers. And I should really be able to look at 6t and realize, hey, that's 2 times 3t squared. Like that should be starting to get easier. Plus t, careful, 0 to 3. Make sure you use the variable they used. And then I plug stuff in. So again, have some common sense here and simplify. Don't just write it down really fast when it's this simple. 3 cubed over 3 would be 3 squared, which would be 9, plus 3 times 3 squared, 27, plus 36, minus parentheses, check, plugging in 0, but you see this time they are all 0. But always check, because on the problem above, 0 did not give me 0, right? So it's always better to write minus 0 like that so that I know, hey, I checked it. I didn't mess up. It actually is 0. Then you just get your numerical answer, which I think is 72. And then it's miles. And again, make a note to yourself, the reason that was distance, total distance traveled, is because that velocity is positive on that whole interval. If I were to do it in a different interval, it might not be the case. Okay, but this one's positive for 0 and up. Okay, so now here's the huge thing. This is talking about the accumulation function again, and we talked about this earlier. It's this initial value that everybody forgets. That's the part that we struggle with. So they're telling you that if we take a function and we define it as an integral, and the integral goes from a constant to x, okay, then I'm going to add the initial value, so whatever's gone on up to a, so f of a, and then I integrate from 0 to x, or a to x. You will totally understand this way better in a minute, because we're going to do a whole bunch of these, okay? It'll make sense. But that initial amount is what people tend to miss, okay? And they do the integral, but they forget that, and then that messes everything up. So let's see how that all works and stuff. So if we go back to the problem we just did and say, okay, got water in the tank, but now they're telling you, hey, when we started, there was 120 gallons of water in there. Now I want to know how much water is in the tank in 5 minutes. Well, it looks very similar. This part's what we just did. However, what do I need to include? 120, because initially there was 120. Initial value does not always mean 0. It could have been, they could have said, after 2 minutes, there's 120 gallons. And then how much water is there after 5 minutes? You do 2 to 7, or 5, or in 5 minutes total, be 2 to 5, or they said in the next 5 minutes, it'd be 2 to 7. But so it's whatever at the beginning, whatever goes to this number, okay, whatever value you have up to that point, then plus all the rest of it, okay? And so that would be 120 plus this 2/3, blah, 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 right? If it was a calculator question, I wouldn't have a mess like that. I'd have an actual number, right? But it's not a calculator question, so just leave it. And then what units? Gallons. Because it's still gallons. Nothing has changed. The difference is they're telling you that there was a certain amount of water already in the tank. Okay? So now for B, let's say we do the second example, but now they're saying it's already 57 miles away from where it started. It's traveling in a straight line. After 3 hours, how far away is it from where it started? So you would have the initial value, 57, plus the integral from 0 to 3. So that'd be 57 plus 72, 129 miles. Okay, so that's just an example of using those functions with worded problems. Now the rest of these problems we're going to do, we're going to look at graphs, which is super this exact type of problem, this example 3, very, 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 very common to be one of the free response questions, okay? Or part of one of the free response questions. Super common. So let's read carefully everything that it says, because this is what you have to be careful about. So they're saying f is the graph of the function shown over on the right. That graph is called f. G of x is defined to be the integral from 0 to x of f of t dt. Now, a lot of students start freaking out and going, well, but that's f of t, this is f of x, so they're not the same. But they are, because the notes that you should have taken on the second fundamental theorem of calculus tell us that if we take the derivative of the integral from a constant to x, we simply get that function with the x plugged in. So we could use x inside right now, and then it's just a different x that gets substituted. That just makes it confusing. So we just use t or a or p or q. It doesn't matter. We use something else so that we know, okay, that's f of x when I'm done. Okay? So what I'm saying that's super important to learn is I need to recognize that if I do the derivative of g, that means to do the derivative of the integral from a constant to x of this f of t dt. Now, this shouldn't be shocking that if I take the derivative of the integral, I just get back what I started with, right? I mean, your derivative of the antiderivative ought to be back to the original. But it's not always. But it is as long as this integral goes from a constant to x. Okay, it can go from any constant. It can be 15 to x. It doesn't matter, any constant. And the top has to be plain x. Otherwise, you have to use the chain rule. So then it would be the function inside times the derivative of that thing that wasn't plain x. Okay, we'll get into more of that later. So this is actually f of x. Now, the reason I need to say that is for questions that we're going to have later. It doesn't matter where I say it on the question, but at some point I have to tell you that I figured out that this graph, which they told me was called f, is in fact the derivative of g. Okay, so I'm going to write it right here. F of x equals g prime of x. That's important because remember how much we struggle with looking at a picture and not recognizing that it's the derivative, right? We mess up and start treating that as the function. Okay, so now let's look and see what this function is. So the function says g of x is defined to be the integral from 0 to x of f of t dt. So if the input is 0, g of 0 is going to be to integrate from 0 to x. Well, x is 0, so I plug 0 in. What's the integral of 0 to 0? 0. Because what's the width of that rectangle? Nothing. Okay? Remember the whole point of how we found area and stuff. Okay? There's no width there. Next. If I plug in 1, that means I'm doing g of 1. So again, 1 is plugged in right there. I integrate from 0 to 1. That's the definition right here. Right? That's what they tell me g is. The integral from 0 to 1 of f of t dt. So go over here and look at the graph. How are we going to find the integral from 0 to 1? Find the area, because this is all segments, right? So this is stuff we just literally add up, find the area. So this is easy. What is it? 2. Okay, let's do the next one. So we plug in 2. That means we have g of 2. So we're going to integrate from 0 to 2 of f of t dt. So we know that we got 2 here. What do we get here? Not 2. Well, okay, but a triangle that we can find the area of easy, which is 1, right? So we get 3. Now, let's think about it for a second. If I integrate from 0 to 2, I'm accumulating. This is why integration's accumulation function. I already knew the first part was 2. I'm adding 3, so my area is 5. But I don't have to keep doing that. Like, I didn't even have to write that here. Because now my next problem, I'm plugging in 3, so I want g of 3. I'm going to integrate from 0 to 3. Well, I already know how much is 0 to 2. That's 5. So all I have to do is add what happens from 2 to 3. It's accumulating. So what's the area from 2 to 3? 2, because it's 4 times 1 and then half of that. So 2 plus the 5 I already had, I get 7. Now we're going to skip a little bit and we're going to go over to 6. So we want to know what is g of 6. So g of 6's definition, based on the formula up there, is integrate from 0 to 6 f of t dt. Well, I already know what 0 to 3 is. That's 7. So then I just have to figure out what happens from 3 to 6. And then what do I do with this part from 3 to 6? Subtract it because it's underneath, so it's negative. So going from 3 to 6, you're going to have 1, 2, 3, 4, right? Like you can just sort of, it's pretty easy to count because of that goes right through the diagonals of those squares. But it's negative plus the 7 I already had. So it's 3. Now, I already know that all the way here to 6, if I do all of this area, that whole accumulation is 3. So all I have to do is add this next area, which is, nope, negative 1. It's negative, though. Be careful, because it's net area. It's underneath, so it's negative. So I subtract 1, and I'm done. G of 7, integrate 0 to 7. But think of it like that, exactly what it is. It's an accumulation function. Okay, so as I know some of the numbers, I just keep adding on to that or subtracting if it's underneath. So those are those values. Okay, question B, which is on the next page, but I'm going to say right here, B says, on what interval is g of x increasing? So here's the super important statement here. What did I just say, g of x, how does it relate to this graph? This graph is the derivative. How do I know if a function is increasing or decreasing? From the derivative. Derivative is positive. Remember, this is that stuff that I'm telling you should write down in your composition book if you don't know it. I don't care about the shape. I care about above or below. That's it. So when I'm looking at this graph, when is g increasing? 0 to 3. Because g prime, not it's, never say it's, use automatic 0. G prime, which equals f of x, greater than 0. I would always state that. I'd go ahead and say that those are the same. Because we're going to give a reason every time, right? Remember, that doesn't matter if it asks you to justify, you're always going to do it. So you're going to say 0 to 3, which you can write in a lot of different ways. Let's write it, we can write it this way, or it's x, I guess, technically. T was just for the stand-in variable for that integral, okay, so we weren't plugging the same thing in. Oh, only we shouldn't include 0 and 3, right? Remember, for integrals, we don't include the ends, so better to say 0 to 3, and then again, what was our reason? F greater than 0, very good. G prime equals f of x greater than 0. Now, technically, I've already said that g prime equals f of x one time in the problem. So I could just say g prime greater than 0, and it would be okay, because I've already said that those two things are the same thing. I just think it's better, the more times you write that, the more you're going to see what's going on, okay? Next question, where does g have a maximum? So how does a derivative tell us where the maximum is? Changes from positive, not increasing to decreasing. The derivative changes from positive to negative. So go back to the picture. Where does it change from positive to negative? 3. So what value, where does it have a maximum value would be x equals 3, and our reason would be since g prime, which equals f of x, you just told me, so literally write that, changes from positive to negative. Okay, next question says sketch a graph of G. So we're going to just plot the points that we just put on that table, which you have right in front of you. So we're just going to literally plot those points. So the first one was 0, 0. Then we have 1, 2. Then we have 2, 5. And then 3, 7. And then 6, 3. We're going to go ahead and fill in a couple of other points real fast. 7, 2. So how can we fill in a couple of points? Well, what if I wanted to know what it is at 4 and 5? What do you know happens at 3? Biggest, right? This is the max. So I already know it's 7. So all I have to do is go back and look at my picture and say, okay, what if I want to know the answer at 4? What's it going to be? 7 minus a half, right? So it'd be 6 and a half. So if I want to get a better graph, I'll go ahead and put 4, 6 and a half. And then 5 would be 6 and a half, because I already found that out, right? Minus this part that's underneath, which is how big? No. 1 and a half. I've already subtracted that first half, right? So minus 1 and a half. So we're going to get 6 and a half minus 1 and a half, 5. Then draw this. Well, when we draw it, we don't know perfectly how the concavities and stuff. Just draw it the best you can based on what looks reasonable, and it's a curve. Okay, because we didn't know enough. We're not going to go through all the concavity information and all that. This is just to sort of get the idea. Okay, so again, super, super, super common question. They will not give you this table. They're just going to say g of x equals that integral. Now tell me where g is increasing or something, okay? Or they'll say graph this or find these values. They'll say find g of 0 and g of 2. Then you just do that part, okay? So you just do that to answer it. Okay, let's go to the next one. So now we're going to figure out what happens if the limits of integration change. So what happens if, so first question, we're going to do the same thing we just did, but go 0 to x, new graph. Then we're going to go from different value on the bottom and see what difference it makes. Okay, see what the difference is. So here, f of x is defined to be the integral from 0 to x of f of t dt. The graph over here is f, as it says right here, right? So now what do you know that it is? It's the derivative of capital F, right? So again, somewhere I would write that. So I would know that f prime of x would equal the derivative of the integral from 0 to x of f of t dt. Fundamental theorem of calculus, the derivative of the integral from a constant to x, you just plug in x. Okay? So I've now just determined that the derivative of capital F is in fact this graph right here. That's important, okay? I need to find that. Now I've said that, I don't really have to say it again, because now I can just use either one of those. So now let's complete the table of values that are here. So if x is 0, you're going to be integrating from 0 to 0, so you're going to get 0. And I'm not going to write all the integrals out, just to hope, I assume you all see, right? You're just plugging it in. So the next one is 0 to 1. It's going to be 1/2, right? Because it's the area from 0 to 1. Next is 2. That's a 2, because it's 1.5 plus the half I already had, or look at the whole thing when you're that small. If I go to 3, it's 2 that was already there, plus just this part right here, right? Yep, and 4.5 is fine. When your decimals are, this is all dealing with graphing and things, so you want to do that. Now it's 4.5 plus 3.5, right? That part. So write that arithmetic down if we can't do it in our head. Okay. All right, so that's what I get. So I'm going to erase this because we're going to use this graph again, okay? But that's what I'm trying to let you see. Okay, let's go ahead and answer some more questions. So B says, what is the domain of capital F? What are the X values that I know stuff about? 0 to 10. I don't know anything else. This is all I have. So the domain is 0 to 10. Inclusive this time, though, right? Because it's domain. And there is a value at 0 and there is a value at 10. It's not where it's increasing, it's what's the domain. Okay, now it says use the idea of area accumulation to complete the graph of F, and we're going to plot all the values. Okay, so get blue. If you don't have blue in your container, get something closest to blue. There should be something bluish. You're going to do green for the other one. I would not use something I could not erase, but it's up to you. Because even colored pencil doesn't erase great, but it does erase, right? At least it does erase a little bit. All right, so get a blue, and you'll need a green for the other graph in a minute. If you're already digging, you might as well dig out green also. Do what?
Blazing blue and emerald green.
There you go. Blazing blue and emerald green works. As long as there's a blue and a green. Your what? It's still stuck? Nice. Well, guess what? You can't go anywhere. So, you're attached. Okay. All right. So let's go ahead and plot these 5 points that we have. And then we'll continue on. You'll get the idea here. So we're using, it told us to do it in blue, right? Blue is the first one. Yeah, in blue. Okay, so we're going to do 0, 0, 1, 1/2, 2, 2, 3, 4.5, 4, 8. Okay, so let's find more points. I don't really need to write the integrals out. I can figure this out, right? From 0 to 4, the answer is 8. So now just add at 5. How much do I need to add? 3. So that would be 11. So at 5, I'm just up here at 11. Now I know all of that is 11, so I add how much? 1 more, so that would be 12. So at 6, I get 12. Quit worrying about your shoe right now. Worry about graphing. Okay, now what? If I go to 7. Subtract a half. I think that's not exactly a half. We're going to call it a half because it's not really, right? Because that's not, it's more than a half. So call it half-ish. Subtract half-ish. We're not trying to be perfect here anyway. That's okay. Now, if I go 1 more over, so now I'm subtracting more from that, from where I already was. I subtract some more. How much do I subtract? Well, we're going to call that 2-ish, because it's not exactly right, but we'll call it 2-ish. So we'll subtract so that we're about in the same spot. Oh, if we can do it right here. Really, that's probably at 9. That would be at 9 because of the way we know how to know what that triangle would be. But again, this is close enough. And then between 8 and 9, that's another 2-ish, right? So we're going to go down to, I think it's a little more than 2 again, like that one was, right? That was a little more than 2. That's why we're down at 9. So a little more than 2. So just go past a little bit, past the 7, underneath the 7 a little bit. And then another half-ish. That should put you at 6, because that's what it's really, the half is about a 3/4. Okay? And then what else? Is that it? Yeah, because that's 10, right? Okay, so now let's connect that with a nice little smooth curve. All right. Now we're going to answer some more questions, and then we're going to talk about what happens when the bottom is not 0 and compare the two. So where is the 0 of F? When does that capital F equal 0? At 0, okay? What is the total change in F? Well, what does total change mean? It means f of 10 minus f of 0, being capital F of 10, right? Minus capital F of 0. That's the total change, correct? And minus the beginning. Well, isn't that exactly the integral from 0 to 10 of its derivative? You'd get the antiderivative, plug in 10 minus plugging in 0. So what's the answer? What did we get at the end? 6. How does the total change in F compare to the net area? Same thing, right? Because if we did do f of 10 minus f of 0, we would have taken 6 minus 0, which would be 6, which is the same exact thing as the net area. So in other words, those two things are the same. What is the maximum value of f? What was the highest? 12. Where does it occur? X equals 6. Now look at the picture. Why did we know that should be the case? Because this changes from positive to negative there, and that's its derivative. Okay, that's the f's derivative. So it should be where the maximum is. And then it says, what is the range of f? So if we look at f, the range is 0 to 12. And I'm just going to use brackets, or you could use y, or you could use capital f of x, or whatever. Okay, so now we're going to use same graph, but we're going to answer questions for g of x, and g of x goes from 3 to x, not 0 to x. Okay? So we're going to go ahead and make a little table for g, because otherwise we're not really, it's going to have a harder time figuring this out. So right here, I think you have room, well, you probably have room right over on the edge on the right where you can kind of make your own little table. So we'll do, I'm going to use green just because we're getting ready to graph this in green, but you can just use pencil. So I have x and I have capital G of x. So this is not f anymore, this is g. Very similar, but what's the difference again? Where's g going? From 3 to x. It still isn't f of x still the derivative. Because the second fundamental theorem of calculus says the derivative of the integral from a constant to x is just to plug in x. So we still have that graph being the derivative of g. All right, so let's start plugging some numbers in before we answer these questions. So first value of x is 0, right? So what's different here?
3.
So it's going from 3 to 0 of f of t dt. So what does that mean? No. It's the opposite, remember? If you have the limits backwards, then you do the area still, but you have to take the negative of the answer. So let's go back and look at the graph. If we go from 0 to 3, what are we going to get for the area? It's 3 times 3 is 9. Take half of that's 4.5. But then it'll have to be negative 4.5, okay? Because we're going the other direction. So this is negative 4.5. Okay, so if I do 1, I'm going to be going again from 3 to 1 of f of t dt. So I'm going to find the area between 1 and 3 and then change the sign. So let's go back. What's the area between 1 and 3? No, be careful. I don't include 0 to 1 anymore, remember? I don't include that. It's from 1 to 3. So it's a little different. So 1 to 3, it's 4, and then negative, because I take the opposite. So be careful how you look at that. So this is negative 4. Then let's do 2. So you'd be integrating from 3 to 2, which means integrate from 2 to 3, take the opposite answer. So from 2 to 3, we get 2.5, and then we take negative. And then what happens at 3?
0.
So there's the answer to the first question. Where is the 0 of g?
3.
At x equals 3. Next question, what is g of 0? Negative 4.5. We just found it because I think the table is an easier way to kind of get the information. What is the domain of G? Still 0 to 10. Because its derivative still goes from 0 to 10. The domain is still 0 to 10. Let me use interval notation to be quicker. What is the total change in G? So what that means is G of 10 minus G of 0. So we haven't found G of 10 yet. Let's go ahead and find G of 10. We're going to need to find some other ones anyway, but we know what G of 0 is, so let's find G of 10. So G of 10 would mean, okay, when I go up to, this one's kind of weird, okay, to do, because I have to know what's going on over here, which is negative, and then add whatever happens here. Okay, so it's kind of a weird way to look at it. So what are you going to get? Well, what is if we go all the way, if we go from 3 to 10? No, some's positive, some's negative. Now I'm going 3 to 10. So now there's no negative, no change in signs anymore because the function goes 3 to that. So what's this area? 1, 2, 3, 4, 5, 6, 7 and a half. So this is 7.5. What's this area? This underneath part. Well, it's a triangle that is how wide? 4 by 3 and then half that. So this is 6 but negative. So that's going to be 1.5 plus the 4.5. Or not plus 4.5, but minus 4.5, right? For a G of 10. Which is going to be 1.5. So I'm going to put that in my thing. Negative, or not negative, it's positive. 1.5. Is that right? Because that's positive 1.5 plus the 4.5. I mean, minus the, what did I say? Plus? No, minus the 4.5, but minus a negative 4.5. So anyway, so it ends up being, yeah, that's confusing. Okay, the difference is 6. Okay, that's what's important here. Okay. G of 10 is integrating just from 3 to 10, which is 1.5, okay? So I'm going to take 1.5, G of 10 is 1.5, minus negative 4.5, right? G of 0 was negative 4.5, that makes 6. Because G of 10 is just 3 to 10. I didn't need that other part that was shaded. What is the maximum value for G? Well, let's figure out where we should see the maximum. Where should we see the maximum? At 6, still at 6, doesn't matter, right? Still at 6 because that's where the f, the derivative, changes from positive to negative. So it's still going to be at 6, so we're going to have to figure it out. So let's add to our table here. I need to know what's happening at 6. So let's go back and look. So at 6, remember, again, you got weird stuff going on. You got 7.5, but then this other part was negative. But you don't really need to do that. That's not how we do it. We go from 3 to 6, right? That's the definition. 3 to 6 is the integral, so it's 7.5. So we're going to get, at 6, we're going to get 7.5. Because remember, the definition of this function is starts at 3. We just got weird stuff on the left of that, because that was stuff that was backwards. So the maximum value is 7.5. Where did it occur? At 6, still same place. What is the range then of G? Oh, nope, negative 4.5 to 7.5, right? Because the first value at 0 was negative 4.5. Now we're going to sketch that one in green. So let's go ahead and sketch these points and then we'll add on to that. So we need to sketch in green. So I'm going to erase my little messy stuff here. Let's see, that was a half, right? Okay. So what's the first point? What's 0? Negative 4.5. So put a point. Then at 1 we had negative 4. What do we have at 2? Negative 2.5. And 3 was 0. Because we started, this was 3 to 3, right? So now, as I integrate and do everything across, I'm just, forget all of this stuff over here. The definition was 3 to x. So if I want the value from 3 to 4, I just need this area, which is 3.5. So 4 is at 3.5. From 3 to 5 is going to be 3.5 plus 3. So that'll be 6.5. And then at 6, we'll be going from 3 to 6. So that's 6.5 plus the 1 more. So 7.5, which we already know is the maximum, right? And that should be. Now take that 7.5 and subtract this a little more than a half-ish, right? So it's a little more than a half. So go a little bit underneath the 7 there. Then subtract another 2-ish. It's a little more than 2, so that's where we get down, I think, exactly to 4. Oh, no, that'd be the backwards way, a little less than 2. Sorry, I was counting the other way. Because 1, 2, so it's a little bit underneath. Then you go 2-ish again, so you get around here. And then you just do a little bit less, so right there. Now, connect that with a smooth curve. And what do you notice?
They're the exact same. Well,
Except,
similar graph.
no, they're the same except shifted. But doesn't that make sense? Think about it. When you take derivatives, does anything matter if you have vertically translated anything? Because derivatives are slopes of the tangent lines. So the function itself is a little different, but they are simply the same shape, just shifted. So if we change that bottom number, all we're going to get is a vertical translation. So that's what the question is asking. Describe the relationship between all f of x if you go from k to x. And you change k. So it's all, they're just going to be vertical shifts.
Vertical shifts
Of each other. No. Each graph is a vertical shift of each other. It depends on the, we don't know how much the shift is. Depends on the function.
Oh.
But every capital F, okay, every definite or every antiderivative is simply going to be different vertical shifts of each other, depending on where I start, that k. So if the k started at 1 versus starting at 1.6 versus starting at 4 versus starting at 8, it's going to give me the same shape. What point has to be on the graph of any graph? Now, when they say what point, they don't mean the 0.10. Like, it's not a number for both, but there is something that will always be there. Where that number is what? That's the k, right? That's the bottom. So you're always going to have k comma 0. You're always going to have that because whatever you start on the bottom, you integrate to that number, you're going to get 0, right? Because 0 to 0, 1 to 1, 2 to 2, 3 to 3, 1.5 to 1.5. So k 0. And that's, you can just say because like a shorthand k to k of anything is always 0, right? If I integrate from k to k. So whatever the numbers are, it doesn't matter. If I integrate from one to the other, same number to itself, I just get 0. Okay, so in general, this is organizing all this. As k takes on different values, where k again is this part right here, as k takes on different values, the graph is, it should be is, but vertical, they're vertical transformations of one another, each containing the particular point k0, so whatever that bottom number is. Even though the lower bound changed, is f prime still equal to ft for all of them? Yes, because f prime is slopes of those lines, and that doesn't matter if I shift it up and down if the shape is the same, right? So this is important. Okay, important connection between those things. That's why we need to know that. Okay, we are going to finish this because this will be much quicker. We don't have to do a lot of adding and subtracting. So, or we have to do simple adding and subtracting. Okay, so assume that we have this. Now, this is that part. F of negative 3 is negative 8. This is the way I think of it. You may think of it differently. Okay, but I kind of think of it like this. I think of it like, okay, they're telling me that if I were to add up all the area up to negative 3, the answer is negative 8. That's kind of how I think of it. So if I'm going to integrate, if I'm going to do f of 2, I know that as I get up to negative 3, the answer is negative 8, and then I just need to do the rest of it up to 2. So that means, and you're going to write all this down because this is important. So it's negative 8 plus 10 plus 26. Don't shortcut that because you need to see what we did. The negative 8 comes from, okay, up to negative 3, this is the answer. It's negative 8. Now I have to do the rest of the areas from 0 to 2. Now, what is that number? But I definitely would write negative 8 plus 10 plus 26 for my notes, for sure. So what if I want to do f of 6? Well, I already know, right, I already know this answer all the way to 2. That's the same idea. This whole thing all the way up to 2 is 28. So all I have to do is subtract 8 and add 14. Because it's an accumulation function, right? I already knew what was going on all the way up to 2. I just need to continue to put that on there, so that makes 34. Now, here's a different question. What is f of negative 5?
What did you just do?
So stop and think about it. It's not something you should just be able to answer immediately. You got to think about what's going on. If I say f of negative 5, that's to the left of negative 3. So it means you have to subtract that, right? So what's the area up to negative 3? Negative 8. And then instead of adding 18, subtract 18 because it's backwards. This 18 is the integral from negative 5 to negative 3, right? But I'm on the other side. I'm on f of negative 5. Does that make sense? Think of it like this. Adding all the way up to here is negative 8. This is 18. I want the rest of this way, right? So I have to take the negative 8, subtract 18. That should give me all the stuff that's on the other side. Kind of. It's weird, but it's the way I like to think about it because it's easier for me. Because if it may not be easier for you, but it's easier for me because otherwise I get confused about, am I adding or subtracting? Is it plus or minus? Is it negative, positive? So I just think they told me f of negative 3 is negative 8. So they're saying if I add from way back here, wherever, okay, all the way up to negative 3, I get negative 8. That's not really what it is, but it's more, it can be considered that, okay? So I add up all the way up here, I get negative 8. But I want just up to negative 5. I don't want to go all the way up to here, right? So I have to subtract off this extra stuff because going up to negative 8 included this 18, right? So I got to get rid of it to give me just this other part.
So that means that negative 6.
Now look at it this way. Now look at it. What if I told you that this up to here was negative 26, and I wanted to go to negative 3, I would do negative 26 plus 18, and I would get negative 8, right? Just keep at it, because I can't stress enough how much this is for sure on the AP test multiple times, okay? It's a really important concept, okay? Really important idea to be able to look at graphs and understand how that all relates. There's other ways that you can think about it. That's just the way I like to think of it, because it helps me see it better than just memorizing some stuff. Okay, since the area under F is positive from negative 3 to negative 1, so if we look at the graph from negative 3 to negative 1, that's from here to here. It's definitely positive. So what does that mean about capital F? It's increasing. Exactly. This is its derivative. I have to know that, right? This was the derivative. So therefore, F has to be increasing there. Now, read this one carefully. Since the area under F accumulates at an increasing rate, in other words, its rate of change is positive. So what is that? What derivative is that? Second derivative, because the derivative of the derivative is positive. F must be, it works like you think. So positive is up, concave up. So looking at the graph, do you see why it's saying that? Right? This is increasing. It's accumulating. It's increasing. It's an accumulation function. As I go from negative 3 to negative 1, I'm getting more area, right? I'm accumulating more. It's increasing. So that means the original function's concave up. Next question, if we go from negative 1 to 2, so now what's happening? If we go from negative 1 to 2, what's going on? It's decreasing. Its rate of change is decreasing. It's still positive. It's above the x-axis, but the rate that it's accumulating is going down. So that means it must be concave down, because it's decreasing here. So it's concave down. All of those things, super important to understand how all these things relate. It does not say at all that capital F is decreasing or anything. It's saying that because the rate of change, which is the graph, is going down, so its derivative would have to be negative, original function concave down. Okay, all of those things super important. We're not going to sketch the graph, so we'll leave that blank. And that is the end of the notes, and now you can all speak again. Well, not wow.
Are you still recording?
Yes. What are you supposed to say?
I can't believe